So good night, everybody. Thanks, Shiva, for the introduction. I assume, I'm not sure, I got kicked out pretty early when Zoom crashed. But yeah, so tonight I'll be presenting on an introduction to continual learning. So first, I'll just go over the agenda. First, we'll go over the definitions, benefits, and major challenges involved in continual learning. Then we'll look at some specific applications that can benefit from continual learning. Then we'll look at the types of approaches there are for CL in neural networks and the current state of them, a comparison. And then lastly, we'll briefly go over some of the routes for future possible improvements in these methods. So continual learning is about the incremental development or the incremental learning of increasingly difficult behavior from these continuous streams of data in particular. So it's kind of like if you think of normal machine learning as batch processing in a way, then CL is like the real-time processing version of that. The overall goal here is to preserve the core knowledge that was extracted from the information from the data, while extending it or being able to extend it to new variations of data, and in some cases, even new classes or tasks entirely. So you'll sometimes also see it be referred to as lifelong learning or incremental learning. So why should we care about this, especially when you could just periodically retrain your models, depending on your cases or your needs? Well, firstly, it's quicker to adapt to changes or variations that weren't present in the original data set. And in cases where the data, the classes, or the tasks change frequently or is difficult to prepare ahead for, this adaptation could be very convenient. And these are the cases where most concerned with, where the change is frequent and it's impactful. On the next slide, we'll talk about some examples where situations like this occur as well. It also saves on the computational cost of having to frequently retrain these models from scratch to cater for new changes, especially since a lot of the time these are relied on for these rely on shared resources, shared like cloud resources for computation. And if the change is wide reaching in your particular area, or if it's very popular, then that affects a lot of other people too. And it could introduce these further scheduling delays and that kind of stuff. So especially for large models, like ones with multiple modalities or multiple tasks, frequent retraining is even less feasible. Like if there's one particular type of input or task that has new cases, to retrain a large model for that would be difficult to justify, but that one case would suffer in performance until it's resolved. In some cases, also the amount of data being produced could just be so much that it's difficult to collect and prepare for scheduled offline training. The main point for this one is that when the data set reaches a certain size, the model's update speed may not be able to keep up with the real-time data generation speed in your environment. Or for privacy reasons or compliance reasons, maybe it's even impossible to collect that data for offline use. So to extract useful knowledge from it and move on without storing it could also be a useful benefit in cases, especially when you're dealing with learning on edge devices, for example. So just to quickly go over some general areas that can make the most of these benefits, and to talk a little bit about some recent papers that are actually applying them. Firstly, there's robotics. Perception here would include stuff like object detection, recognition, image segmentation, which are all normal or common computer vision tasks. However, in like a new environment for a robot, it might need to learn new objects, and some may be like just variants of already learned objects, like a new pose, different lighting, different color, different angle, stuff like that. So it should be able to ideally leverage what was already learned and adapt quickly using that. Regarding reinforcement learning, a lot of RL problems exist in these complex or ever-changing environments. Some cases, even the reward function might change. Or sometimes, even if the objective stays the same, that change in environment or state may only be partially observable. So there's a lot of different forms for change when you consider the practical uses of RL. And these frequent changes would be where continual learning comes in. It would essentially be trying to help the agent recognize the changes and update the representations it needs to make decisions in these environments that change. For example, reinforcement learning in financial markets. The goal here is clear and it doesn't change. You want to buy low and sell high. That's the gist of it usually. But there can be these massive external factors, something as big as COVID or something as scheduled as earnings announcements, or shift in online sentiment. These things would change the state of the environment the agent is working in, and all of a sudden that agent needs to adapt with only partially observable information. So in addition to needing to figure out the representations for making decisions in these dynamic environments, in robotics, there's also often limited compute and memory resources. And the combined effect of all of these things is why it's often considered a very natural application for continual learning, where it can make updates using these limited resources in a frequent and needed way. That being said, limited compute and memory is also the case for learning on edge devices, like we talked about before. So for example, there was a paper earlier this year that focused on applying continual learning to traffic flow predictions on edge devices. Secondly, there's healthcare. So the rate of data generation here may not be as high as what we just talked about, but the data is still large, complex, and it comes in many different forms because you have so many different devices and methods for collecting it. So it's very computationally expensive to retrain the large models that would come out of these situations with multiple modalities and lots of different classes for them as well. There's also the labor or implementation costs regarding the ML ops around retraining these models that are in production if it needs to be frequently done. So there was a paper a couple of years ago that looked at continual learning applied to chest X-ray classifications. And just for that one type of modality and that one area or like a focus, there were dozens of classes of diseases that it needed to learn. So in healthcare also, it's generally difficult to curate these comprehensive data sets to begin with because of the regulations, consent for use forms, and all these things adding additional steps on top of the sheer variety of the data you're working with. But even still, even if you have a good primary data set, the model may not perform that well on the new samples that it will have to face because, especially for diseases, the demographics of the patient population is so important as a factor, especially with those diseases that have genetic associations, and you need to consider for patients that have comorbidities and those things that may not be represented in the original set. Therefore, this could be one way to help combat that lack of diversity in the typically available data sets you would find and allow places to just start with what they have and learn the representations needed as they go. So in addition to regulations and consent, due to the stakes of privacy and security regarding medical data, its availability even may be limited to like a certain time period when it's like, even when you're allowed to use these data sets, you may only be allowed to use it or hold it for a certain period of time, or you may only be able to store it at a certain location. And all these limitations also affect the possibility of regular scheduled retraining in a feasible way. So this diagram here is from a paper that discussed the clinical applications of continual learning. And they described some of the different ways the continual updates of models could be integrated with existing healthcare procedures. So this chart is about the cases where clinical results are going to happen regardless. So you could consider like a case where a regular diagnosis would take 3 months, but through using some ML model, as soon as the input is available, you get an earlier diagnosis in less than 3 months. So it's a bit of a safer step towards these models that change, because it doesn't take away heavily from the standard of care. And you also need to have an additional step in between for labeling data, because it's going to get labeled on its own. So this is a nice, safer use, since the model prediction isn't massively relied on, but still a benefiting factor and deals with the types of changes that we're concerned with. So I've mostly talked about continual learning and reinforcement learning and image classification with these examples. And honestly, these are the areas that see the most attention, but recently there's been growing interest in applying it to other areas like sequence models, language models, recommender systems as well. So to explain the main challenges in continual learning and some of the approaches, it helps to go over some ideas of how CL in the human brain works, because this is also a common source of inspiration for approaches to CL in neural networks. So it helps to explain the intuition there as well. So there's the complementary learning systems theory. And here, the hippocampus is normally associated with short-term memory. The prefrontal cortex, which is within the neocortex, is usually associated with long-term memory of core concepts and key knowledge. And the consolidation from short-term to long-term is believed to be through these internally generated replays of experiences. And these replays could be when you're unconscious, like when you're sleeping, or when you're conscious. So we have these two systems that use these rich set of principles to balance two objectives. And these two objectives are stability and plasticity. Stability refers to our ability to remember important core knowledge and skills, while plasticity refers to our ability to learn new things and take advantage of what we already know to adapt to new things or learn them quicker. However, while learning these new things, there's the risk of causing the loss of previous or important information or knowledge. And this is called catastrophic forgetting. And it's the main reason why this balance is so important. And in neural networks, it's a very big challenge. And it's the reason why a lot of approaches need to take certain precautions or measures in their methods, because they're, unlike in people, it could be caused by just modifying important parameters in the model when you're trying to learn new stuff. So in humans, catastrophic forgetting very rarely happens. And when it does, it's only under extreme cases. So just to better exemplify what this problem is, it was observed in a study on the word recognition ability of Korean-born adults who are originally from Korea because they were born there, but were adopted by French families during the age of 3 to 8. And well, they had no residual knowledge of the Korean vocabulary. And the brain imaging data during the experiments showed that when they heard or saw Korean, it was no different to hearing or seeing any other foreign language to them. So their ages here are important to note as well, because when you're younger, there's a lot more plasticity than stability going on. And as you grow older, that plasticity decreases and your stability increases. But this is just a general example of observed interference, like what catastrophic forgetting is about. So that's one of the big challenges. But before we go to CL and neural networks, it would help to just define some of the different scenarios it's applied to a bit better to understand its scope and what it looks at. So firstly, there's the task incremental scenario, where an entirely new type of job can be learned, but it requires maintaining these identifiers, like I minus 1 and I, which is a bit tedious during inference. Some approaches for the task incremental case, they like to maintain separate models for each task because they're so cleanly cut and separable, but having a single model that branches out with different heads is another way papers go. And I think that's a bit more in line with the overall goal of CL, because then tasks can benefit from learning other tasks, although in that case, forgetting also becomes a bigger problem to share in the earlier stages. Secondly, there's the class incremental scenario, where the task itself remains the same, like image classification, but yeah, the task remains the same, but new classes can be learned. And the main difference here is we no longer need these identifiers. And lastly, there's the domain incremental scenario, where both the task and the classes stay the same, but the change comes in the form of new forms of data or shifts in the distribution of the data. So now you need to be concerned with things like distorted images or noise or variants that weren't originally catered for. So that's domain changes. So in terms of approaches, they generally fall under these three big categories: regularization, dynamic architectures, and those inspired by the CLS theory or memory replay part of it that we talked about earlier. These aren't just completely separate categories. They could be methods that combine different aspects of them, or they could be subcategories that focus on a certain piece. But generally, these three categories are a nice way to introduce the different types of approaches, I think. So the regularization approaches generally work by imposing these constraints on the training of new stuff. And these constraints are done through penalty terms in the loss functions or modifications to prevent catastrophic forgetting. And as you might imagine, these constraints would also impact how well the model learns. So there's that trade-off on performance as well. So for that reason, there's a good amount of methods that combine this with another approach. So for the sake of time, I won't go into individual methods except one or two maybe, but on the side here, there are one or two examples. I think I left the color black by mistake though, but it says elastic weight consolidation and learning without forgetting are two of the more commonly used or seen regularization approaches. So dynamic architecture are the second general category, and these modify the network design, like they modify the actual design of the network dynamically as it tries to learn new concepts without actually touching or affecting the older parts of the network. So it might expand or add new units as its way of consolidating new information or new knowledge. But since our goal is to continually learn, and we saw in some of the examples, resources are limited, practically this isn't a very scalable choice. So I don't hear too much about these methods alone either. The examples I've left in black here by mistake are PACnet, PathNet, and HAT. So lastly, there's those that are based on CLS theory or memory replay, or both sometimes. So here there'll be two networks, one modeled after the hippocampus with a fast learning rate, and one modeled after the prefrontal cortex with a slow learning rate. And they would represent like the long-term and short-term networks. And then for consolidation, it would replay samples. So there's a memory replay part of it. It would replay samples from the short-term memory network, like one samples it once used for the short-term network, and it would replay it for the long-term network to learn from or train with. But keeping hold of these samples, like over time from a continuous stream, especially the older ones, it can add up in terms of the demand for memory. So, and we talked about a lot of the benefit being for situations with limited compute and memory. So some methods use pseudo rehearsal, where it would form this representation of those older samples and then generate new ones when it's needed. So some newer papers would use stuff like GANs for this part of it. And then when it has those generated samples, it would weave them in with the new data and use that for training. So there's a fair amount of variety in this third category. The methods, they don't all use both CLS and replay. So MIR, which is one of them here, uses only replay. iCall and GEM use some regularization techniques as well. And well, Fairnet uses CLS and replay, but it's also a very interesting method because it adds this third system that's modeled after the amygdala. And the amygdala is the part of the brain that's responsible for processing the memory of emotions, especially fear, since the memory of fear is just crucial to survival. So Fairnet has the usual two CLS networks, and then it uses this third one to decide whether or not we should use the long-term or the short-term network for inference. And this allows it to recall new information easier without increasing forgetting and without forcing the system to remember, yes, less useful stuff. So Fairnet is a pretty cool one, I think. All right, so I left this black too. So I use this browser extension that changes everything to dark mode. Like it inverts the colors. So I think when I was using that extension, some bits of text were white, and that's why I mistook them for white when they're actually black when I turn it off. Yeah. So a couple months ago, there was a very comprehensive review of some of the popular methods for CL applied to online image classification specifically. And I thought including a bit of that would be a good way to help show the current state of these approaches. So this here is a set of methods that are run against image data sets, and they're fed in a continuous way. So they split the overall data set into these disjoint sets of classes and fed them in like smaller amounts, like 5 or 10 at a time, that kind of thing. So a couple of these are standard data sets, and I'll talk a bit about the third one in a little bit. And yeah, the results are taken at the end of the overall training. Also, in evaluating continual learning, there's certain additional metrics and experiments that are recommended in addition to runtime and accuracy for evaluating these things. So here, there's also a metric for catastrophic forgetting, but you would also see things like back transfer and forward transfer being looked at, since we care about how well the model is leveraging previous knowledge to learn new stuff. Also, just to clarify something that kind of confused me a bit when I first started reading about this stuff is if you compare the results of this to like the state-of-the-art models in a normal offline deep learning setting, they're miles off, right? We're getting like 20 something to 30 something here, but efficient net gets like 90 plus on the CFAR 100. But that's not really a fair comparison, because in that kind of situation, there's hyperparameter tuning or use of extra data from pre-training and a lot of optimization on this still set. And even then, if you were to put those good models in a continuous setting where there's very frequent and significant change, which is where CL is meant to be used, you won't get that level of result. So it's important to keep that in mind when we're in this kind of online continuous setting. That being said, GDOM tries to do exactly that. It's an approach that tries to place a state-of-the-art model in this type of setting to act as a baseline for the methods that are actually designed for continual learning. So it stands for greedy sampler and dumb learner. And it greedily stores samples in memory as they come from the continuous feed. And at each test time, it'll train a model from scratch using those samples that are in memory. So I think in the case of this paper, they would have used ResNet as the model behind GDOM. And so this way it makes for a very good baseline, not the most practical for actual use because of its demands in terms of memory, because it's storing everything that comes in, and also runtime. But it still acts as a very good baseline for comparing. And one that performs very well still compared to the others. As you can see for these two, GDOM is the one that's in blue and it still gets the highest accuracy for most. MIR and iCall do get competitive results on the first two data sets, but it's worth mentioning that MIR beats it by a decent margin in the Core 50 dataset, which is important to note because Core 50 is the most complex dataset here, and the most realistic for the case because it's the only one that's specifically designed for continual learning. It stands for Continual Object Recognition with 50 classes. So in terms of these results, you could say in overall, they're closing the methods that are designed for CL are closing the gap to this baseline. Whether or not these results are actually close to being acceptable in real settings, I'm not really sure. I guess it would depend on the application and its tolerance, but it's definitely a step forward. So possible routes for further work in this space. The results of the proposed methods are good, especially for some of the older ones. They're very good in their confined environments, but we need more results that closer resemble real situations like what the Core 50 dataset tries to do, or results from testing methods in specific practical applications, because this could also help us understand where which method shines and why, or it could also just generally help us explore the potential of continual learning and motivate work on improvements in the different areas, because it's pretty wide reaching or spreading. So kind of like what the clinical applications paper was doing, because so far it's largely been a very theoretical space, although it does seem to be growing in popularity and application over the last couple of years. Secondly, the benchmarks for CL in other areas, as well as like having offline baseline comparisons, like what GDOM tried to do. So that's a very important step forward as well, because the comparison we went through was for image classification, right? And even though image classification and reinforcement learning are the two most focused areas for this space, it was still a recent comparison. So for other areas like NLP, sequence models, Rexis, stronger consensus on benchmarks and the specific experiments that we do for CL would be useful. So even though there's been advances in certain areas, generally CL still doesn't have the robustness and flexibility it needs to really be practical in the amount of scenarios it can be. So with the previous successes of using inspiration from the brain, psychology, cognitive behaviors, maybe trying to further bridge that large gap between CL and neuroscience is one way forward, by making more efforts that build on top of these observations from humans and animals to address the key obstacles in the area. More fair net approaches, basically, is another good way forward, especially in unsupervised learning. There's just generally less options there. Some people argue that by trying to base these models on how we think humans think is inducing a level of bias and not the way forward, but we've seen some success like this in other areas, like with the hierarchical nature of CNNs being loosely based on the brain, or specifically in how we look at rewards and reinforcement learning. So I still think it's a fair path, especially for unsupervised learning. And other than that, as I'm sure some of you would have noticed, there's similarities here to some other related fields in ML, like transfer learning, meta learning, auto ML, one-shot learning. So taking the perspective of these fields is another way forward to try. For example, there was a paper from some people from Amazon Research a couple of years ago that presented a reference architecture for continual auto ML. So they had this vision for an auto-adaptive ML system that relies on continual learning and maintains itself in production. So like an intelligent layer above your normal ML system. And they took a very practice-focused approach to the way they designed and laid out the components of their architecture. So they had like a part that was meant for addressing the data that comes in from the feed, making sure it's not too much for the rest of the system to handle. And then they had another component that looked at detecting distributions, shifts in the distribution of the data to see if it requires some degree of retraining, rollbacks, that kind of stuff. So it was a very different approach from a lot of the more theoretical ones we've seen so far. These are the references, mostly survey papers for the more specific areas. And that's about it. Thanks for listening. Are there any questions?
Yeah, thanks for that, Reshawn. Very interesting stuff. And I think it will become more and more important as we produce data at a faster rate and have a need to adapt to this data as well, because yeah, I mean, dealing with these big data sets, as I said, you can't really retrain each time. So I see this as an interesting area to do research in. You know, I kind of look at it in a slightly different point of view, because it's similar to what you do with signal processing, right? You have a signal coming in, you want to maintain some of the characteristics from the past because it has more data in there to give a robust estimate. But of course, you want to take into account the new information. So yeah, I think some stuff in signal theory might be able to, or signal processing might be come in handy here at some point in time. Yeah, interesting stuff. No more questions. Thanks.
Okay, thanks. I'll try to check out the signal processing stuff. It sounds pretty relevant, like I said.
Well, the interesting thing is you have a signal here, just like for signal processing. So I'm not sure if you got this from one of the papers or what, but the chart you have here is really signals, yeah.
It looked, I guess, like continual to me, so I just picked
Yeah,
this
well, yeah.